Okay, welcome back to linear algebra. In this first lecture of section 6.2, we're going to look at a procedure that can take any basis in an inner product space and replace it with an orthonormal basis. All right, so it's called the Gram-Schmidt procedure. So to start us off here, let's suppose that we're given some orthogonal set of non-zero vectors in an inner product space. Okay, so I've got a vector space V, it's got an inner product on it, I've got this set S, it has k elements. Any two of those inner elements have inner product equal to 0, and no one of those elements is the 0 vector. Okay, so if you take an element in the span of that set, that is, you can write it as a linear combination of elements in that set for some scalars in the field, then if you take that element y and take the inner product of it with any of the elements in S, so I'm just replacing y with this linear combination. I've got the inner product with Vj. The inner product is linear in the first coordinate, so I can push that sum through, pull out the scalars. But this is an orthogonal set. Yeah, so if the indices I and j are not equal here, that term is 0. And if they are equal, well, then I get the length of Vj squared. Remember, Vj is a fixed vector, an element of S. so all the terms in this sum are 0 except for one of them, and that one non-zero term will be Aj times the length of Vj squared. And since we said Vj is not 0, I can divide both sides of that equation by the length of Vj squared to solve for Aj. So this is kind of the punchline. If you have an orthogonal set of non-zero vectors in an inner product space, then when you write something in its span, the coefficients that you use to write that linear combination are computed in terms of the inner product, according to that formula. So that actually comprises a proof of the first theorem in this section, theorem 6.3. It just kind of says exactly what we just did. If you take an orthogonal set of non-zero vectors, so no vector in there is 0, then any element in the span, the coefficients that you need to write it as a linear combination are the inner product of that element with the ith basis vector divided by the length of the ith basis vector squared. Or I'm saying basis vector, I mean element of the set S. Cool. A couple of corollaries of that. In addition, we assume that the set S is not just orthogonal, but orthonormal, so every element of it has length 1, well, then these denominators down here are all equal to 1. So the formula just sort of simplifies. So corollary 1 is one of the reasons why orthonormal sets are so nice. When you want to write something as a linear combination of elements of an orthonormal set, the coefficients that you need are found by taking inner products. One more bonus of this is that any orthogonal set of non-zero vectors is linearly independent. That's the second corollary. Why is it linearly independent? Well, if you take a linear combination of those elements in S and you get 0, well, the theorem implies that the jth coefficient in that linear combination is the inner product of 0 with Vj over the length of Vj squared, but that's 0. So if all the coefficients are 0, the set was linearly independent. So that's kind of a nice bonus. If you have an orthogonal set of vectors, none of which are the 0 vector, then that set is automatically linearly independent. Okay, so those two corollaries, I think, both indicate that orthogonal sets are extremely useful, right? It makes the linear algebra problem of finding the scalars in a linear combination easy to do. Let's look at this example that I took from your book. You can stop the video and verify that this set S consists of orthogonal vectors that each have length 1. So it's an orthonormal subset of, let's just call it R3. So you can stop the video and check that out, or you can go back, as the author said, that it was worked out in example 8 of section 6.1. So it's an orthonormal subset of R3. Our corollary says it's linearly independent, so it's actually a basis. It's a basis for R3 because it's got the right number of elements in it and they're linearly independent. So it's an orthonormal basis. And let's just pick an element of R3, this vector 2, 1, 3. So if I wanted to write that vector in this basis S, then the corollaries above say, well, I should take the inner product. So if I take the inner product of, say, 2, 1, 3 with this first basis vector, Well, what are you going to get? You're going to get 2 plus times 1 plus 1 times 1 plus 3 times 0. That is 2 plus 1 or 3. And you multiply that by the square root of 2. So there's the computation. Likewise, the inner product of 2, 1, 3 with the second basis vector is going to be 4 over root 3. And with the third basis vector, it's going to be 5 over root 6. So the theorem is saying that those are the coefficients. You can stop the video and check it out. If you take 3 halves of that, 3 over root 2 of that first basis vector, 4 over root 3 of the second basis vector, and 5 over root 6 of the third basis vector, and add them all up, you get the vector 2, 1, 3. Okay, so that's much faster than solving a system of linear equations to find those coefficients. So why do we get to take that shortcut? Because we're working with an orthonormal basis. Orthonormal basis, you don't have to solve a system of equations to get the coefficients. You just take some inner products. Okay, so that kind of begs the question, like, well, how can we arrange to have an orthonormal basis? The good news is you can always do it. You can always take any linearly independent subset, in particular a basis for an inner product space, and you can replace it with an orthonormal set that has the same span. That orthonormal set is linearly independent. So in other words, you can always take a basis for an inner product space and modify it into an orthonormal basis. Okay, in the process, I'm going to write this down later, but that's called the Gram-Schmidt process. Let me illustrate the general idea with a couple of small examples. So suppose that my given linearly independent set is this set S, and its elements are called W. So I'm drawing them in the picture here. It's kind of a busy picture, but W1 is this long vector drawn in black. W2 is this shorter one drawn in black. They're clearly linearly independent in the picture. W2 is not a scalar multiple of W1. So what my goal is, I would like to produce a new set, S prime, with two vectors, V1 and V2, and I'd like those two vectors to be orthogonal. I want their inner product to be 0, and I'd like them to have the same span as the span of S. Okay, well, you can kind of see in my picture how I'm going to define V1 and V2. In fact, I'm just going to take V1 to be W1. Yeah, so I'll just take it to be the first vector. And then V2, you can see in the picture, I've labeled it right here. V2 is a vector that when I add it to some scalar multiple of W1, I get the vector W2. Or solving that equation for V2, I want V2 to be W2 minus some scalar multiple, but we need to find the C. I need to find the C. What do I need about that C? Well, I want them to be perpendicular to each other. All right. So I'm going to take those expressions up there and start off by saying, like, well, what would it be? What would I have to say about C if I wanted the inner product of V2 and V1 to be 0? I want them to be orthogonal. So I'm just replacing V2 with how I defined it and replacing V1 with how I defined it, and then use the linearity of the dot product. All right. I can solve that equation for C. If W1 is an element of a linearly independent set, it's not 0, so I can divide by W1 inner product itself, that is the length of W1 squared. So I get the vector C, or excuse me, the scalar C is the inner product of W2 with W1 over the length of W1 squared. Okay, so this new set is orthogonal by construction and hence linearly independent. Okay, and then if we look at these two equations, V1 is certainly in the span of W1, V2 is in the span of W1 and W2. So that means the span of the set consisting of V1 and V2 would be a subset of the span of the W's. But we already said that this set S prime is linearly independent. So if the spans are subsets of each other and they're both spanned by two sets, linearly independent sets with two elements, they have the same dimension. So that means they're actually equal. So we achieved our goal. Cool. If you started off with, say, 3 elements, W1, W2, and W3, we'd kind of proceed the same way. Let V1 be W1. Let V2 be W2, subtract off that same scalar multiple of V1. And then kind of proceeding by analogy, if you let V3 be W3, subtract off the kind of analogous scalar multiple of V2. So I take W3 inner product V2 over the length of V2 squared times V2, subtract the same scalar multiple of V1. Then those three equations that I've just been talking about make it clear that this span is going to be a subset of the span of the W's, because the V's are all linear combinations of the W's. And I claim that this new set S prime of those V's is orthogonal, right? I've already shown above that V1 and V2 are orthogonal. So in order to prove this claim, I just need to show you that the inner product of V3 and V1 is 0, and the inner product of V3 and V2 is 0. So I've just got the computation written out down here. If you take the inner product of V3 and V1, you have to be able to look at the definition of V3 up here, and I'm just pushing the inner product through linearly. So when I take the inner product of V3 with V1, I get the inner product of W3 with V1, that's the first term, minus the inner product of the second term with V1, but V2 and V1 are orthogonal, so that inner product is going to be 0. And then minus the last term's inner product with V1. Well, the inner product of V1 with itself is the length of V1 squared. So you get that coefficient times the length of V1 squared. But now those cancel, and you're left with inner product of W3 and V1 minus itself. That's 0. Okay, I think it's obnoxious for me to talk through all this, so I'm just going to say stop the video and verify that V3 or inner product with V2 is also 0. Okay, so S prime is an orthogonal set. By the same reasoning, the dimensions of the spans have to be the same, so those spans actually have to be the same. Nice. So what I was just trying to illustrate there for the case where there's 2 or 3 vectors is this result called Theorem 6.4. Theorem 6.4, it has a name. It's called the Gram-Schmidt process. Gram is like that, G-R-A-M, and then Schmidt is S-C-H-M-I-D-T. This is the Gram-Schmidt process. And what does it say? It says if you take any set of linearly independent vectors in an inner product space V, and you define a new set S prime, as we did above, the first element of S prime is the same as the first element of S, and then the subsequent elements are formed by taking the elements of S and subtracting those scalar multiples of the previously constructed elements of S prime. So you do that for k between 2 and n. Then the result is that S prime is an orthogonal set of non-zero vectors with the same span. Okay, so this is a way of taking a linearly independent set and producing an orthogonal set of the same size that has the same span. Okay, let's take a look at the proof of it. You're going to want to write down this equation 1. I'm going to be referring to it heavily in the proof, but we won't be able to see it very long. So we're going to proceed by induction on the number of elements in the set S. Okay, so if S only has one element, then we just take S prime to be that same element. It's orthogonal trivially, vacuously, and clearly has the same span. So the base case is just kind of trivial. So now let's suppose that this theorem holds whenever you have linearly independent subsets with n elements in it for some n greater than or equal to 1. Okay. So what do I mean by that? I mean, if you give me a linearly independent set with n elements and I construct S prime according to equation 1, then S prime is orthogonal and it has the same span. And now I'm going to take a linearly independent set with n plus 1 elements and suppose that I've constructed S prime according to that equation 1. So my goal is to show you that this S prime is orthogonal and has the same span. Okay, so if I denote by Sn the first n elements of S, well, that certainly is also linearly independent, yeah? And its Sn prime would just be S prime, take away that last vector, Vn plus 1. So it is constructed from Sn via 1. So I can use the induction hypothesis. I can say that Sn prime is an orthogonal set and its span is the same as Sn. Okay, so that's most of the work, the first n elements. But let's look at the last one. If you take that last Vn plus 1, it can't be 0 Because if Vn plus 1, you have to look at equation 1 to see this. Maybe I should scroll back. If Vn plus 1 was equal to 0, then I could write Wn plus 1 as a linear combination of the W's with smaller subscripts. That's contrary to S being linearly independent. So Vn plus 1 can't be 0, right? If Vn plus 1 were 0, Wn plus 1 would be in the span of Sn, contrary to S being linearly independent. Okay. By the induction hypothesis, Sn prime is an orthogonal set. So to show that S is orthogonal, I just have to show that this new vector, Vn plus 1, is orthogonal to the other V's. Okay? Because if you take two subscripts, say I and j, where I is also less than or equal to n, then we know that those are elements of Sn prime, which is orthogonal. Okay, so this is sort of like the argument that I did above, but just when n plus 1 was 3. So I just do it. I just take Vn plus 1 and take the inner product with Vj. Using formula 1 and the linearity of the inner product, that's going to give me the inner product of Wn plus 1 with Vj minus pushing the inner product through the sum. I would get those coefficients and the inner product of Vi with Vj. Right? But in this sum, I is between 1 and n. So by the orthogonality of S prime, all of these things are equal to 0 except for when I is equal to j, right? Vi and Vj are orthogonal unless I is equal to j. So in this sum of n terms, the only non-zero term happens when the index I is equal to j. So what am I going to get there? I'm going to get Wn plus 1 Vj's inner product, length of Vj squared times 1 over it times itself. They'll cancel. So I just end up getting the inner product of Wn plus 1 with Vj minus itself. That's 0. Okay, so that shows that S prime, all of n plus 1 V's, it has no non-zero vectors, and it's linearly independent by corollary 2 because I just showed that it was orthogonal. Right, so S prime is orthogonal. It has no non-zero vectors, so it's linearly independent. Clearly, its span is a subset of the span of S because every element of S prime is a linear combination of elements in S, right? So if both sets are linearly independent and they have the same size, then they have to be, the spans are equal to each other, excuse me. S and S prime are not equal to each other. That's a typo. What I mean is that the span of S prime is equal to the span of S. Cool. Okay, so that process is called the Gram-Schmidt process. You replace if you take it takes an arbitrary linearly independent subset of an inner product space and produces an orthogonal set with the same span. If you take each one of those non-zero vectors in S prime and divide them by their length, then you produce an orthonormal set. It's linearly independent and it has the same span. Cool. So if you put all that together, if you take a non-zero finite dimensional inner product space, then that proves that it has an orthonormal basis, beta. And moreover, if you take some orthonormal basis beta, then for any x in that set, you can write x as a linear combination of the basis vectors just by taking inner products. So just to really quickly kind of sketch the proof of this, apply Gram-Schmidt to an arbitrary basis. That gives you an orthogonal and hence linearly independent set with the same span. So it gives an orthogonal basis. And then replace every element of that orthogonal basis with a unit vector with the same direction. So then normalize. Gives an orthonormal basis. Squeezing this in because I don't have much room. The last statement of the theorem follows from corollary 1 up above. Nice. Let's look at an example. Let's take this basis beta over the degree 2 or less polynomial space, P2, over the real field. And I'm going to define, I'm not going to prove it's an inner product right here, but you can stop the video and try to prove that this is an inner product. But I'm going to define an inner product by saying the inner product of two polynomials is the integral from -1 to 1 of their product. Okay, let's apply the Gram-Schmidt process. Let's orthonormalize this basis, if you'll let me use that verb. So if you just want to kind of use the same exact notation as the theorem, I'm thinking that 1 is W1, X is W2, X squared is W3. Okay, so what do? Well, we let V1 equal W1. V1 is W1. What's its length? Well, its length squared is the inner product of it with itself. So that's the integral from -1 to 1 of 1. That's just 2. Okay, so when we go to normalize this thing, we're going to divide V1 by the length of V1 and divide it by the square root of 2. But before we do that, let's find the other V's. So V2, just following the Gram-Schmidt process, V2 should be W2, that is X, minus the inner product of W2 with V1, right? V1 is 1 over the length of V1 squared, and you multiply that by V1. I've got the calculation down here. The inner product of x and 1, it's the integral from -1 to 1 of x. That's 0 because x is an odd function. So it turns out that V2 is equal to x. V2 equals W2. So the Gram-Schmidt process so far has not changed either one of the two vectors. That's okay. It's okay. It just means that x and 1 were orthogonal to begin with under this inner product. How do we calculate V3? Well, V3 is W3, and then you take the inner product of W3 with V1 over the length of V1 squared times V1, subtract the inner product of W3 with V2 over length of V2 squared times V2. Okay, so we've had to compute those things. You have to compute them as you go because to compute a new V, you need all the previous V's. Here I've done some side work. The inner product of x squared with 1 you can check is 2/3. The inner product of x squared with x is 0. So I'm just plugging that in, 2/3. We said the length of 1 squared above was 2. 0 divided by I don't care is 0. So there's our V3. It's x squared minus a third. Okay, so what have we done so far? Those polynomials, if you wanted me to match the notation of the theorem, that's an orthogonal set. You can stop the video and check that the inner product of any two of those things, two distinct ones, is 0. But it's not orthonormal because those don't have length 1. So let's compute the lengths. So I'm skipping some of the details here, but I'm just taking the inner product of those vectors with themselves. So for U1, well, I already computed its length squared is 2. So its length, I'm going to take, sorry, V1's length squared is 2. So its length is square root of 2. So my unit vector U1 is I'm taking V1 and dividing it by its length. 1 over the square root of 2. Similarly, U2 is V2 divided by its length. The length of V2 squared is 2/3. So its length is the square root of 2/3. When you divide by that, that's like multiplying by the square root of 3/2. For this guy, if I included the details, to compute the length of our V3, you have to take the inner product of it with itself. So I multiplied that polynomial x squared minus 1/3 by itself. You integrate that from -1 to 1. You can check the details. I got 8 over 45. Okay, so my third vector, U3, is V3 divided by the square root of that thing. So I've just sort of done the algebra there and pushed it through. So there's my U3. Cool. So what is this thing? Those U's form an orthonormal basis for P2. So I'll let you check that the inner product of any two of those things is 0 if they're different and 1 if they're the same. So it's an orthonormal basis. Nice. Just as sort of some terminology, and maybe it's interesting to you, if you apply the Gram-Schmidt process to the entire basis for the polynomial space, so you just kind of keep doing this, each one you produce a new one, then those things that you get, that orthonormal basis, are called the Legendre polynomials. So we just computed above the first three Legendre polynomials. I'm using a subscript here that matches the index. So in particular, in my notation above, U1 was L0, U2 was L2, U3 was U2 was L1, U3 was L2. I kind of like the index to match the degree of the polynomial. So the Legendre polynomials are by definition the resultant of applying the Gram-Schmidt or orthonormalization process to the standard basis for the polynomial vector space, with the inner product as defined above, that integral from -1 to 1. So as a little challenge to you, I worked out, but I didn't include any of the details, what the next Legendre polynomial is. See if you can produce it. You can stop the video and see if you can work through those details above. It's the best way to kind of see if what I'm talking about is making any sense. See if you can produce the next Legendre polynomial. Nice. Okay, just kind of continuing along here. If we took that work that we did above, so I'm going to take an arbitrary polynomial in P2, not arbitrary, but this one, 1 plus 2x plus 3x squared. And maybe I want to write it as a linear combination of that orthonormal basis we just found above. Okay, so these are the same U1, U2, and U3 that we derived above. All right, so how do we do that? Well, Theorem 6.5 says if you want to know the coefficients, you take your vector, it's f of x in this case, and you take its inner product with the elements of your orthonormal basis one at a time. Inner product in this context means take the integral from -1 to 1 of their product. So if you multiply f by u1, remember u1 is just 1 over the square root of 2. Here's your f. I'll let you check the calculus. So that's the coefficient of f. That's the coefficient of u1 if you're going to write f as a linear combination of the u's. You want to know the coefficient of u2, you got to take u2. Maybe you remember u2 was the square root of 3/2 times x. Here the author is calling the variable t. There's your f. Stop the video and check the integration. That's the coefficient of u2. For u3, you have to take your u3. That was the square root of 5/8 times 3t squared minus 1. Multiply that by the f. Do the integration. Okay, so if you just throw those coefficients, 2 root 2, 2 root 6 over 3, 2 root 10 over 5 in front of the u's, you can check out, they'll add up to f. Again, much easier than solving a system of linear equations, taking advantage of the fact that we have an orthonormal basis. Here's a nice little corollary of this. You guys remember to write the matrix of a linear transformation. You have to find the coefficients of the image of each one of the basis vectors. Well, if you have an orthonormal basis on an inner product space and you want to write the matrix of that linear operator, let's call the matrix A, then what would be the ij entry of that thing? Well, the ij entry is the coefficient of vi of the image of the jth basis vector. But what we just said, if you want to know the image of the jth basis vector's coefficient on the vith basis vector, you dot it with vi. All right. So that's just saying you take t of vj. What's the coefficient of vi when you write it in the basis beta? Well, it's the inner product of vj and vi. So again, writing down the matrix is kind of easy. You just take t of each basis vector, and then you dot it with each basis vector and keep track of the indices, and that's what tells you how to write down what's in the ij entry of the matrix. It's kind of a cool application of that. We're going to end just with a little bit of terminology. These numbers, these coefficients, if you take an orthonormal subset, and it could possibly even be an infinite orthonormal subset, like for the polynomial spaces or function spaces, then by the Fourier coefficients of a vector relative to that orthonormal subset, I just mean the inner product of x with an element of that thing. So y here ranges over the betas. So these coefficients that you compute with inner products are called Fourier coefficients for historical reasons. So above, when we worked out an orthonormal basis for P2 under that inner product integrating from -1 to 1, we got that the orthonormal basis were those things, those first three Legendre polynomials. Okay. So if I wanted the Fourier coefficients of, say, this polynomial 1 plus 2x plus 3x squared, that's what we worked out above. We took those inner products and got root 2 root 2, 2 root 6 over 3, 2 root 10 over 5. So those by definition are the Fourier coefficients of f in that orthogonal set. Okay, we computed that above. What's the history? Fourier was a French mathematician, Jean-Baptiste Fourier, who was interested in kind of approximating functions with Taylor-like series, but instead of using Taylor series and coefficients with factorials, he was interested in approximating things where the coefficients were sines and cosines. So he was trying to write down, superimpositions of waves to describe any function. So in general, or more specifically, if you take a continuous function, and I'm thinking about that orthonormal basis for the continuous functions that we talked about. So f sub n is by definition e to the int. E to the int, you remember, is sine t plus I times cosine nt. All right. So the Fourier coefficients of a continuous function are by definition the Fourier coefficients for the inner product where we integrate f times g, sorry about that, divided by 1 over 2 pi. So I'm just going to kind of squeeze it in here. But the inner product I'm talking about on the space functions on the interval from 0 to 2 pi, continuous complex valued functions. The integral is, whoops, I forgot my normalizing coefficient, 1 over 2 pi times the integral of 0 to 2 pi of f times g bar, dt or dx, whatever you want to call it. That's the inner product. So the coefficient, if you inner product f with one of these basis vectors, the complex conjugate puts a minus sign on there. So this is just the inner product of f with a basis vector, f sub n, written below. Yeah, so that thing is called the Fourier coefficient of f. Okay, and those are the so-called classical Fourier coefficients because it's kind of where they got their name. So Fourier himself was studying these integrals and using these things. So infinite sums of these CNs were approximations for f over the interval. And then it kind of neatly fits into this linear algebra picture as we've described it here. Okay, so that was kind of a lot, but hopefully you stopped the video and it sunk in a little bit, and I'll see you in class.